Hello, my name is Andrei Poenaru. I'm a PhD student with the HPC group at Bristol in the UK, and today I'm going to present to you a summary of our paper evaluating the effectiveness of a vector-length-agnostic instruction set, which looks at modern vector computation with a focus on ARM SVE. My work is around modern and future architectures for HPC, and at Bristol we have experience with most of the common HPC architectures in use today, including ARM-based CPUs such as the Marvell ThunderX2 and the Fujitsu A64FX, x86-based CPUs from Intel and AMD, and GPUs from the three major vendors. We study architectures from two perspectives. We look at differences between platforms and how to obtain the best performance on a wide range of them, and we do focus studies to understand the depths of individual architectures. One of the architectures we are currently most interested in is the Scalable Vector Extension, or SVE, from ARM. SVE is a relevant architecture to study because of its use in the newest generations of ARM-based HPC processors. Fugaku, the number one supercomputer in the top 500, uses Fujitsu A64 processors which implement SVE, and in our own Isambard 2 we hope to add some of the same processors later this year. At Bristol, we've been studying SVE since it was announced a few years ago. We think it's very important to get an early start, not only to be better prepared when the hardware arrives, but also because early experiments help improve toolchain maturity. Using emulators and simulators, we have worked directly with ARM and a number of supercomputer vendors to identify and fix many pre-release issues, which has led to stable and performant toolchains from the very first released versions. SVE also prevents a novel research problem. Because vector length isn't fixed, but rather each implementation can choose its own, it is important to understand the impacts of this choice on application performance. To study SVE, we took a collection of mini apps that we've worked a lot with in the past. These are mini apps that we understand very well, both in terms of the code and their performance profiles, and each of them is representative of a wider class of HPC applications. Stream is the de facto memory bandwidth benchmark. Build is a compute-bound computational chemistry mini app. T-Leaf and Cloverleaf are structured grid applications. Neutral is a Monte Carlo particle transport application. MiniFMM is a task-based mini app that implements the fast multipole method. And Megasweep is a benchmark we developed based on the kernel of the Snap proxy app for deterministic particle transport. We're interested in the vectorization characteristics of these applications, so we ran them on a single thread, a single MPI process where applicable, with all the I/O, initialization, and finalization stages removed, such that we only captured data about the core kernel. We used a combination of static and dynamic analysis tools, and the ARM instruction emulator, or ARMI, was the main tool we use for instrumentation. ARMI allows you to run SVE applications on regular ARM v8 hardware, but it also lets you add custom instrumentation to record data about how your application performs. You can also simulate SVE applications. The Gem 5 simulator, for example, has an SVE version, but because these are orders of magnitude slower than real time, it makes it harder to evaluate real-world problems. The first step in our analysis was to investigate how the application is vectorized, both on SVE and on the other current generation vector platforms. We selected the main computation loops from the applications and looked at the compiler's ability to vectorize them in the three main HPC compilers, GCC, Cray, and ARM and Intel on the respective platforms. Each of the applications is presented as a row in this table. Immediately to the right, we list the number of core loops analyzed and their percentage of runtime on a real core of ThunderX2. Then, the compiler's performance, in terms of number of loops vectorized, is clustered by platforms. First is SVE, then Neon, the previous generation vector instruction set from ARM, and the one that ThunderX2 uses, then AVX. The results were the same for both AVX2 and AVX512, so they are shown as a single cluster in this table. Each cell is color-coded according to the percentage of loops vectorized. While the Intel compiler vectorized the highest number of loops on x86 platforms, the compilers which can run on all the platforms studied, GCC and Cray, vectorized at least as many loops on SVE as they did on Neon and AVX, and sometimes even more. This supports SVE as an instruction set that is well suited for scientific compute. Please note that the Cray results are obtained from a pre-release version of the Cray compiler for SVE. We then took each application and looked at the dynamic count of instructions executed using custom instrumentation through the ARM instruction emulator. This graph shows the instruction usage data for BUDE, the Molecular Dynamics mini-app. The leftmost cluster shows the data for a run in which vectorization is explicitly disabled. The next one shows data for a neon target, such as the Thunder X2, and the remaining clusters each correspond to a selected SVE vector width, which can be given as a parameter to the emulator. Within each cluster, the colors correspond to different types of instructions. The light green is scalar ARMv8 operations, the orange is neon, and the other colors are all different classes of SVE instructions. BUDE is a compute-bound application which makes good use of vectorization, so the number of executed instructions decreased as the vector length was increased, because each single instruction processed increasingly more data. Cloverleaf, the fluid dynamics mini-app, showed a different profile. First, not all of the code is vector code, so a significant portion of scalar instructions are executed even at wide SVE lengths. Most of the scalar code is from outer loops in loop nests, because the compiler only vectorized the innermost loops. Second, while all three compilers showed similar behavior at narrow widths, the number of instructions executed by the version compiled with Cray decreased much faster with vector length, suggesting better vectorization. With the Cray compiler, the number of scalar instructions also decreased with vector length, which may seem counterintuitive but can be explained by looking at how these compilers vectorize loops. ARM and GCC generate vector-length-agnostic code that can run on any vector width, but with Cray, the width needs to be set at compile time. With this information available, the Cray compiler generated scalar instructions for most of the loop control flow as opposed to SVE instructions. But the number of times these were executed still depended on how much data each vector instruction processed, thus resulting in a correlation of scalar instruction count with SVE width. For most of the mini-apps, regardless of what percentage of runtime was spent in vector code, when vector instructions were executed, the vector registers were fully filled. But in SVE, each instruction is predicated per lane, so it is possible to run vector instructions where any number of elements are masked out. In the worst case, this can mean executing vector instructions that only process a single useful element, thus gaining no benefit from this suboptimal vectorization over scalar code. We observed this effect to various extents in MiniFMM. Looking at the dynamic instruction count for MiniFMM provided a first hint at the issue. Vectorization does decrease the total instruction count up to 512 bits, but using larger vectors brings little benefit. Vector code is still being run at all lengths, but the number of instructions was very similar at 1024 and 2048 bits compared to 512 bits. This happened because even though wider registers were available, they were not being filled with useful data, and many of the lanes were masked out. This graph shows a histogram of the number of bits active in vector operations, grouped in 128 wide bins. A higher bar means more accesses had a number of bits active that falls in that bin. In each column, the last bar shows the percentage of operation in which all the lanes were active. When the vector registers are 128 bits wide, for example, the only way for an access to have between 128 and 255 bits active is for it to have exactly 128 bits active. Data is not shown for the Cray compiler because MiniFMM's build system does not support Cray. We can see that up to 512 bits, most of the accesses use the full vector width available. However, at 512 bits, already only a little over half the accesses use the full width, as opposed to more than 80% of the 128 bits. Going up to 1024 bits, some operations use more than 512 bits, but very few utilize the full 1024 available. At 2048 bits, the histogram is virtually identical to the 1024 one because the additional vector width is not utilized. This MiniFMM example highlights that with SVE, because of the per lane predication, it is not enough to check that vector instructions are being run when analyzing performance, because it is possible for those operations to only use a small portion of the throughput available. Finally, in our paper we looked at how SVE was used for memory accesses. One of the new features in SVE compared to Neon is non-contiguous memory accesses in the form of gather loads and scatter stores. Of the applications we studied, Cloverleaf and MiniFMM use such non-contiguous accesses. This slide shows Sankey diagrams for the types of memory accesses performed by these two applications. Within each diagram, the widths of the bars are proportional and they all add up to 100% in the total bar on the left. For both applications, most of the memory operations were loads, about a third of which were SVE operations. The main difference is that Cloverleaf only performed a small percentage of non-contiguous accesses, and all the lanes were active the vast majority of the time. In MiniFMM, however, about 8% of all memory accesses were gathers, and in about 15% of all accesses, only a subset of the lanes were used. MiniFMM's usage of non-contiguous operations and partially filled vectors was not a performance bug. Instead, this highlights the flexibility of SVE. Due to the nature of the task-based FMM algorithm, a lot of the operations don't benefit from wide vectors, and the ability to mask out lanes enables it to use at least some of the vector power. In a fixed-width scenario without predication, many of these operations would have been run scalarly instead. With A64FX processors becoming available this year, we will soon be able to analyze SVE performance in a real hardware implementation. In the meantime, we have continued our work on simulated SVE, and we will present a paper studying the effects on cache of wide vectors using a subset of the same mini-apps shown today, at the EAHPC workshop as part of Cluster 2020. This paper not only looks at interactions between wide vectors in different cache configurations, but also investigates the access patterns in non-contiguous memory operations. We gathered all the data for the cache paper using an in-house simulator, but we are building a project that aims to be much more than that, a flexible, accurate, and fast simulation toolkit for HPC architectures. We call this project SimEng, and its first goal is microarchitecture design space exploration centered around SVE, with further extensions planned to support the other common HPC architectures. With that, I thank you for watching, and I encourage you to visit our GitHub pages, where you'll find reproducibility data for this paper, our up-to-date benchmarking scripts and results, and details about our other current work.